mechanisms which will be automated. So compared to a human intermediary, it's cheaper to involve a smart contract, so you don't need to pay fees to the intermediary. The contract is an open and transparent program that fulfills the contract and does nothing else. For example, doesn't peek into your data. And the contract can be made highly resilient to attacks, but at least you know the level of security provided by the contract. Compared to similar technologies that were used in the context of distributed databases, we could say that contracts are rule-based rather than data-based. The collection of rules is transparent and reusable across different contracts. A contract is actually like an active object. A contract may decide to take certain steps. It may initiate and play an active role in the communication. It may integrate and fuse data from multiple sources. So it's more like an active entity compared to a database, which is just storage of data. However, around 1994, there was no blockchain. So at this point, the idea of smart contracts was proposed as a concept independently of the ledger. It was not until 2013 that Ethereum combined the two concepts together. So the contract layer in different systems has different features. So we have not seen Hyperledger yet, but we can already compare Bitcoin and Ethereum. So on Bitcoin we have some simple scripts. In Ethereum we have Turing complete smart contracts. The programming language in Bitcoin is a script programming language. In Ethereum there are actually many languages, like as many as 10 different languages are used for writing smart contracts in Ethereum, but Solidity is the most popular one. And today we'll briefly go over Solidity. So the contracts are executed on nodes, are not executed on lightweight nodes. And the contracts in Ethereum are translated into Ethereum bytecode and executed on Ethereum virtual machine, which supports the Ethereum bytecode. So contracts contain executable bytecode, and they also have internal storage. How are contracts created and registered in Ethereum? There is a special transaction which registers a contract, and that transaction provides the code of the contract and also puts some budget into the contract. And contract consists, it's like event-based programming. Contract consists of many functions, and those functions can be triggered at different times. So there are different types of functions, as we will see today. Execution time is limited by gas, as mentioned. A contract can be so what's the trigger? Well, there is constructor function for a contract, but most of the functions are invoked by RPC, remote procedure call. So they are triggered by other transactions or by other contracts. Can also be triggered by a timeout, for example. So what you see here is an example, right? Where the contract would be stored in the chain-based database. So, there, like in block 3, there is a transaction created transaction. And the transaction would have own Here what you can see is a bit more detailed representation. The code of the contract is secured by the hash of the code, which is stored in the database. So for a contract, you can see the balance, the code hash, and the reference to the root hash of the partition of the contract. And the user, while some other accounts can be contract accounts. There are two types of accounts in Ethereum. So now we can take a brief look at Solidity example. And the example taken from proof of existence contract. Of address version. So this is definition of a type listened to by any client. Get automatically generated getters and setters. Here there is a modifier is a special kind of function in Solidity. What does it do? Prepends to any and it's like a condition. You can see the modifier starts with fire. So if the condition doesn't hold, then the execution of the function is aborted. And the same modifier can be included into multiple functions. This is a constructor instance, which is executed when the contract is created, so it's typical for object-oriented languages. And now this is the core function of the contract, which allows the owner to confirm a document ID with a given content. Here we create the proof created event. It was defined in the previous, and we publish this event to the blockchain. And new function, keyword, very important keyword, because it means it doesn't modify the state. If it doesn't modify the state, and its execution doesn't cost any gas. Only execution of functions which modify the state requires some gas. So these are some of the features of Solidity. Now, what do we need to do with contracts? We need to, after we create a contract, we need to compile the interface to the contract. So we configure the interface. Then we deploy the new contract using a new contract transaction. So transaction. And then so this is how we create a new transaction. Usually you don't need to write all this code yourself because IDEs such as Truffle and Remix automatically compile, deploy, and test contracts. However, using smart contracts doesn't come without challenges. It's a replicated execution. So the same function is executed in many different places. So what are the challenges related to that? The first challenge is non-determinism. What happens if the function is non-deterministic? In that case, it may return different results on each copy or on each node executing the function. So that would be it. Then, if it returns different results, how can we verify the correctness? We are keeping receipts from executing the function. So if each time the function is given different result, what's the point of a receipt? We cannot verify that it executed correctly. The next problem is side effects, right? Imagine that a function does some non-idempotent operation. So, for example, it could be calling some external service, and then suddenly the service would be called 100 different times if there are 100 nodes on the blockchain. Such challenges relate to resolved by interacting with the oracles. What is an oracle? Oracle is an entity external to the blockchain with which blockchain interacts. Oracle usually does some sensing on behalf of the smart contract, and it would know the answer. So it works both directions. An oracle would provide information to the smart contract, and an oracle would also consolidate the requests from different copies of the smart contract. It's called an oracle because it would know the answer. And that definitely helps with invoking external services, because then the oracle would invoke external services only once. That's not all. Next, upgrading and fixing a contract. I mean, how do you usually upgrade the software? You upgrade the software so suppose you fix the bug. Now you have a new version, local version of the software, but the old version is still running. So you store the state. The old version of the software would store the state. Then you would usually bring down the old version for a brief period of time, and then you launch the new version. It's not as simple with smart contracts. What's the problem? The problem is that the smart contract may store some data on the blockchain. And when you launch the new contract, how would the new contract get access to the data stored by the old contract? So there is a need for some sophisticated control schemes. So upgrading contracts is actually a painful operation. You need to be very careful, especially because contracts are prone to bugs. And indeed, there are bugs which are specific to smart contracts, so which you would not see in other types of programs. And today we are going to see some of those bugs. I mean, one direct implication is that you can directly lose money due to bugs. So writing smart contracts may require some economic thinking perspective. You need to consider incentives of the participants. So now we are going to see a few buggy contracts. This contract implements a rock, scissors, paper game. So we have two players. And each player is supposed to, each player joining the game deposits some funds, right? And also provides the value. And finally, when all the players join the game, the contract would check the values and would declare the winner and transfer the funds to the winning participant. Okay, so specifically how it's implemented. There is the init function, which initializes the number of players to 0, and the most interesting function is player input. If number of players is smaller than 2, and the value in the message to 1,000, so 1,000, the two players begin with a 1,000 away price. So each player deposits 1,000, and then the winning player would collect all the winnings. Okay? So if the number of players is smaller than 2 and the value in the message is equal to 1,000, then we proceed with execution. Otherwise, we return -1, means that that's not the correct interface. So we are not proceeding with the game. Okay, so we increase the word with the value of the message. And we memorize the address of the player, and we also memorize the choice of the player, and we increase the number of players. And there is also one final function which is not shown here, which checks the results, the value submitted by all players, declares the winner, and sends the fund back. So that's the implementation. Now it's very simple program, right? Turns out that it already has up to 5 different bugs. So what's the first bug? What happens if a third player joins the system when 2 players have already joined? Here, if the number of players is not smaller than 2, then we return. Instead, we are supposed to transfer the back to the player who could not join again. So that's missing here. And the same problem happens if the bet is not equal 1,000 weight. If by mistake the player sends a different amount, the player would simply lose the amount because the amount is not transferred back. Okay, that's the first pitfall. The second pitfall, the value, the choice here is sent in plain text. Why is it a problem? It can be easily exploited. What happens is that a player may wait until someone else places the bid. Then the player may check the state and would see the bid. I mean, the whole point of rock, scissors, paper game is that everyone is supposed to provide the value simultaneously. If a player is able to see the previously submitted values, then it gives an unfair advantage to the player. So that's a problem with sending the values in plain text. Okay, so what can we do about it? We do the same technique which is used in zero coin, in zero cash. We submit a commitment. We do not submit a plain text value. We hide the plain text, the value submitted is a secret. Instead, we submit, each player would submit a commitment to the value. And only after all values are submitted, only then the contract would request the players to submit the actual value. And then it would be possible to verify that the values submitted indeed correspond to the commitment. Problem number 3. What happens if, in some cases, the participant may have an incentive to abandon the execution? How so? For example, a player may wait until the other player looks at the result, and then the player can guess that the other player is winning, and in this case the player would not be continuing the execution. Why is that? What would the player gain by not continuing the execution? The player would lose the bet anyway. Well, what would the player gain is that the player would not need to pay the gas on executing transactions. So pitfall number 4, there are Ethereum-specific constraints, such as the limit on the size of the call stack. If a function if the call stack becomes too long, the execution would abort. And it turns out that can also be exploited, especially like if the attacker can control the size of the stack. You abort execution at the right moment, and by doing that, you can avoid paying, for example. You won't transfer in the funds. And the 5th pitfall we are going to consider. What happens if we set the reward higher than the block creation reward? If we set the reward in a game higher than the block creation reward, and the miner is participating in the game, then it becomes more important for the miner to get the game reward than to produce a block. So imagine that the miner mines a block, and then the miner successfully mines the block, and at this point the miner would be able to see that the miner would lose the rock, scissors, paper game. The miner may think twice, why would I publish this block? Maybe I should wait until someone else would produce a block, and then I get a second chance of winning the game. So that's yet another problematic scenario, and all of this just for a very simple program, very simple game, right? So now you can think of what happens with real-scale industrial applications. And by the way, this example is taken from a paper called Step by Step Towards Creating a Safe Smart Contract, Lessons and Insights from a Cryptocurrency Lab. So it's, how did they identify all those problems? They actually announced, like they define the game, and they invited students and programming engineers to come to the lab, and then they asked them to implement the contract, and they gave them even sufficient time. And then they collected they also had presentations, they collected the results, and they analyzed the submitted contracts and saw all the problems which were popping up in different implementations. So it was an insightful exercise. Now here we can see a very famous example of the DAO attack. So So it was an attack on Ethereum where a particular organization raised around $150 million before some point in June 2016. And an attacker managed to steal around $60 million from that DAO using the bug which I'm going to explain. So it was a major theft. And then, as usual, there was a discussion what to do with the theft, and there was a hard fork of the blockchain that nullified the effect of the transactions. And of course, some participants were very unhappy because it's a hard fork. Okay, so how did it work? Okay, this is the gist of the DAO. Contract simple DAO, and you can donate funds to DAO, in which case, so manage an account from different participants, right? So if you donate to DAO, then the account would get increased by the value. Okay? And there is a question which just returns the current value of the credit. And then there is a withdraw function. What does the withdraw function do? It checks the current balance, and if the current balance is not smaller than the amount, then it would invoke a callback on the sender, providing the amount, and then it would basically the callback would like notify the sender, yes, the withdrawal is going well, and then the credit would be must be subtracted from the credit. So it doesn't look suspicious at all, right? You check the balance first, and if there is enough balance, then you notify the sender, and then you subtract the value from the balance. Turns out the critical difficulty here, and it's exploited by the following contract. So what does the contract do? Here is the constructor. So in constructor, just memorize the sender. And then the critical function is the one which receives the callback. What does it do? It calls withdraw in recursively. So what happens here is that the withdraw is called recursively before, and that's a critical point, before the amount is subtracted from the credit. And then it would continue to withdraw the funds in an infinite. Well, not infinite, because the size of the whole stack is limited. But it's limited by a very large number. And that's the number of times the attacker was able to withdraw the funds without getting the balance reduced. So it's a very with quite devastating results. Here's another example of security problems in smart contracts. Here's a contract which implements the Ponzi scheme, but it doesn't matter what exactly it implements. And an adversary managed to steal some ether from the contract in the because of the bug in the contract. So initially, the contract was called dynamic pyramid. But during the development of the contract, the name was changed from dynamic pyramid into a different name. However, the creator of of the contract forgot to change the name of the constructor. So, okay, so now of course the constructor doesn't run. That's one problem. But now a bigger problem is that everyone else can invoke dynamic pyramid. What does dynamic pyramid do? It sets the order of the funds to be the center of the message. So it was the intended functionality of the constructor, because the constructor is only called once in the beginning, with the center being the creator of the contract. But now everyone can call this function and set herself or himself as the owner of the contract. So please note that we've seen many bugs today. Please note that none of those bugs arise in an environment other than smart contracts. They are not. They are specific to smart contracts. They cannot arise in normal programs. So this is why people claim that developing smart contracts is more difficult than developing the normal programs. Okay, still on that topic, I would like to say that, okay, so are there tools that test smart contracts for potential vulnerabilities? The answer is yes, such tools are being developed and being improved. However, there are many languages for smart contracts, right? And each language needs a different set of tools. So it's a long process. And the tools today are getting better. But still, bugs can be easily introduced. Now, another analysis I would like to present is some statistics. On different distributions of smart contracts. So in this analysis, the authors looked at all smart contracts deployed in Ethereum for a certain period of time, and they tried to analyze the distribution of transactions, like how many transactions are due to each contract. And they also tried to analyze the balance of contract. What balance, what's the size of the balance in proportion to the size of the balance of the other contracts. So in total, there were about 10,000 contracts, and the total amount of funds owned by the contracts were, I believe, about $50 million. I don't remember the exact amount. But the interesting thing is the distribution. So they observed that very small fraction of the contracts is owning almost all of the balance. And also very small fraction of the contracts is responsible for almost all of the transactions. So it's like a power law distribution, right? So what you see here on the x-axis is the amount of contracts, right? So this is a cumulative CDF. And this is the probability. What you see on the y-axis is the probability of a contract to exceed the value. So it turns out that distributions of smart contracts are heavily skewed in terms of both the balance and the number of transactions. They also looked at the number of code lines per contract. So you can also, here you can see also typical, yeah, I believe it's an exponential distribution, right? So, so almost, or it could be Pareto as well. Almost all, okay, most of the very few contracts number of lines exceeding 1,000, and essentially there is only a contract with the number of lines exceeding 2,000. So right now, most of the deployed programs, deployed contracts are very short. And this is both because of the complexity of writing the contract, but also because of the gas limitations. Because running the contract execution means that one needs to spend a lot of gas. Therefore, in most cases, long contracts are not beneficial. It's interesting that the bytecode length is a bit different from the number of lines. It doesn't look like the exact distribution, though of course the two are similar. So the originally written contract and the compiled contract have slightly different lengths, proportionally. And this is the end of the lecture. I would like to thank you, and I would welcome questions. Hello, hello, hello. 1, 2, 3, 4, 5. Oh, okay. So the second lecture today is about Hyperledger. We are done with Ethereum, now moving on to another system. Or rather, Hyperledger is an umbrella. So it's managing entity as well. You can guess Hyperledger Consortium. After we have Bitcoin Foundation and Ethereum Foundation, we also have a Hyperledger Consortium. And the focus of Hyperledger is different, however. It's not cryptocurrencies. It's permissioned ledger on consortium network. Hyperledger also has an ecosystem of smart contracts, but it's totally different from smart contracts on Ethereum. The focus is on open source, and as mentioned, it's an umbrella. It's not one system. So there are many projects under the Hyperledger umbrella. Fabric is the flagship product. It's a permission DLT with proprietary consortium deployments. Another project is called Sawtooth. It's also permission DLT, but it has slightly different priorities. I'm going to talk about Sawtooth towards the end of the lecture. The third project is called Composer. It's more about smart contract language and development tool, but also how you combine different components to compose combine different components together in a single application. Cello is a framework for running blockchain as a service in the cloud. And R3 Corda is geared towards financial applications. So R3 Corda is a totally separate. Fabric, Sawtooth, and R3 Corda are in a way competing implementations of blockchain, even though they are within the same umbrella. So today we are mostly looking into Fabric, but we'll also briefly talk about Sawtooth. And the next lecture, I'm going to present Corda. Okay, so entities in Fabric. Entities are already quite different from those in Bitcoin and Ethereum. So let's take one step back. In Bitcoin, we have full nodes and lightweight nodes. And full nodes, they are part of the network, while lightweight nodes are not part of the network. In Fabric, we have peers, which constitute the network. So again, like there is a peer-to-peer network, similar to Bitcoin and Ethereum, but of course at a much smaller scale, because a typical proprietary deployment of Fabric would not have more than maybe 100 nodes, compared to a much larger scale of Ethereum and Bitcoin. To remind you, in Ethereum, we have over 1 million of validators only. In a typical Fabric deployment, we only have maybe an order of 100 peers. Then we have clients. Clients are representing applications built on top of Fabric. So clients are not part of the ledger, not part of the blockchain implementation in Fabric. Instead, they are building applications. They're the ones initiating transactions. Now, transactions in Fabric are usually not financial transfers. It's more like let's store this kind of data, or let's update the database. It's this kind of transactions. And finally, we have the order, which is a special entity in Fabric, or it could be a service, could be several servers which collectively act as an order. But conceptually, order is an entity which orders blocks and transactions. And it's separate from peers. Peers do not participate, well, they contribute to the process, obviously. They send information to the orderer, but it's the orderer which decides on the order. So, as you can see, it's quite different. And peers maintain the ledger. Clients do not do that. Orderer doesn't do that. Only the peers. More interesting concepts in Fabric. In Fabric, we have channels. What is a channel? Channel is like a representation of an application. So the same deployment can run multiple applications, or even within the same application, there could be multiple functionalities, and each functionality would have its own channel. So what's the semantic of a channel? A channel is like a partition of participants in the system. So in this example, you can see two channels. The first channel includes two clients and two peers, and the second channel includes two clients and two peers. So the channels can be overlapping, but obviously they are different. Now, what's the point of introducing those channels? Because each channel effectively maintains its own ledger. The communication is done on a per channel basis. The consensus can be done on a per channel basis. The storage of information and updating all the databases, right? Like there is data world state, similar to what we've seen in Ethereum, but in Ethereum, there is just a single database storing everything that's going on in terms of the data on the ledger. In Fabric, you have the storage on a per channel basis. Another interesting principle that we have in Fabric is the plug-and-play principle. It's like, here we can see the standard blockchain reference architecture, which also play an important role in Fabric. And the whole idea is that Fabric provides implementation for each layer, right? But you can configure every aspect of every protocol. For example, you can use Kubernetes clusters. And then you can also re-implement any protocol. So what happens is that for every layer, Fabric has several pre-made implementations, and the administrator of the deployment could make a decision which of the several pre-made implementations to use for a given layer. And not only this, it's also possible not to use any of the pre-made implementations. Instead, you write your own implementation for a given layer. Or you take a pre-made implementation and extend it. And then, at the end, you get plug and play. So, which means that you can take out any implementation, any protocol out of the stack and put your own protocol instead. So it's highly configurable in that regard. It's probably the most configurable blockchain architecture in existence. However, there is a price attached to that. There is enormous amount of flexibility, but in order to exploit it, someone needs significant amount of knowledge, how to configure the system. So imagine IBM would be, Ethereum, Bitcoin, IOTA, Monero, you just download the executable as a client and you configure it, I don't know, within maybe half an hour or an hour, and then you start running. So it's totally feasible for a not so technically inclined person to use those cryptocurrencies. For Hyperledger, I would not dare to do it. Being a professor, I would still not dare to try to configure Hyperledger without someone's help. IBM gives courses 3 to 6 months on how to configure Hyperledger. So, and as a result, okay, so why is that? Because applications of Hyperledger are industrial strength. And the clients are coming from the clients, sending the entities of clients, sending transactions to the peers. They are coming from large organizations and companies and enterprises. And those enterprises, they hire dedicated deployment administrators for Hyperledger, whose entire job is to maintain the configuration of Hyperledger. So it's a totally different model. Some additional features of Hyperledger. There is no native currency because it's mostly not for cryptocurrencies. However, as always, there are some pre-made implementations of cryptocurrencies, and of course, which you can extend and make your own. So everything is possible in Fabric. But everything is possible means that someone needs to do it, or at least someone needs to configure it. There are a huge amount of libraries, of course, in Fabric, but even understanding the libraries takes some time. Another question is what kind of state tracking to provide. There are two principal approaches to state tracking. In Bitcoin, we use UTXO. In Ethereum and some other cryptocurrencies, we use accounts and balances. And there are advantages to each. So, for example, UTXO, operations on UTXO are easy to parallelize because operations on the balance, everything needs to be like streamlined or linearized. All accesses to the balance need to be sequential in order to prevent balance going into negatives. With UTXO, you don't have such a problem. If a user owns 5 UTXOs, each of the UTXOs can be processed and transferred in parallel. So UTXO approach is more parallelizable. It's probably also arguably better for anonymity, because the accounts are more difficult to make anonymous than UTXOs. On the other hand, if a user owns like 100 different UTXOs, then consolidating those UTXOs would require some large transactions, and accordingly the fees would be bigger. The transactions would be bigger in UTXO approach compared to the account approach. So there are also some interesting scalability issues with the UTXO approach. So the trade-off between the two approaches is not entirely clear. And in Hyperledger Fabric, well, you can guess it. You can do everything. You want to go UTXO, you can implement UTXO. You want to do accounts, you can use accounts. There are pre-made implementations and configurations, and there are recipes how to do things. Some interesting information about storage management in Fabric. So in particular, no state tracking is on by default, so that the administrator of the deployment needs to turn it on. It's impossible, of course, to employ one of the provided options. Now, the storage in Fabric consists of two elements. Well, three elements, effectively. There are blocks stored on disk, there's block index stored in a database, and there is a raw state, which is the actual state stored in a database, which can be CouchDB or LevelDB, and there are advantages to each of the two. So that is also configurable. Now, a very interesting element of Fabric, which you don't get to see in other systems, is that blocks may actually include invalid transactions and yet be approved and become part of the ledger. So the ledger in Ethereum, in Fabric, it may include invalid transactions. Why is that? So why is it a good idea to include invalid transactions, and why is it okay to include invalid transactions? That's two separate questions. So what's the motivation for including invalid transactions? The motivation is that the order in Fabric needs to order transactions as fast as possible. So the order doesn't check the validity of transactions. I'll explain how validity of transactions is verified in Fabric. It is verified, but it's not verified by the orderer. So the orderer, whatever it gets, it just orders and puts groups into blocks and releases those blocks as fast as possible. So by not checking the validity, the orderer gets performance benefits. Now the other question, why is it okay? Why is it not okay for the other systems to have invalid transaction? Why is it okay for Fabric? Well, the difference, of course, is the trust model between permissioned and permissionless. In permissionless, if you allow invalid transactions, then there would be so many attacks and so many denial of service attacks. Everyone can get transaction, so the ledger would be in the permissionless blockchain would be totally polluted by invalid transactions if you let it happen. On the other hand, in Fabric, it's a closed environment run by industrial consortia. Okay, so usually they try to debug the programs and the contracts, the smart contracts in Fabric, sort of are usually more debugged before deployment. But there are also other reasons why transactions may become invalid. However, it doesn't happen too often. So the fraction of invalid transaction in a Fabric ledger is limited. So let's take a look at the processing flow. Again, you have a client, you have peers, and you have an orderer. However, peers are actually divided into several categories. You have an endorsing peer, and you have a committing peer. Okay, so it starts from client sending a transaction. To whom it sends the transaction? It sends the transaction to endorsing peers. So it needs to get an authorization. Every transaction in Fabric requires an authorization. From whom? Well, that's totally configurable, as everything in Fabric. So there is such a thing as endorsing policy. Endorsing policy dictates from whom the client needs to get an authorization. And an endorsing policy can be maybe 2 out of 3, or could be majority, could be anything, right? So the first check of validity for a transaction happens on endorsing peers. How do endorsing peers do that? Well, first of all, they see that it's a valid, authorized client who has the right to do this transaction. So there is access control, of course. But not only this. The endorsing peers would check which data would be affected by a given transaction. So they calculate what's called the RW sets, the read-write sets. The read set for a transaction is the list of data items which would be accessed for reading. And the write set is the list of data items which would be accessed for updating. And these two sets are produced by the endorsing peers, and they are sent back to the client, and also signed, of course. So the client should not be able to tamper. As the next step, client sends the endorsed transaction along with the RW sets to the orderer. Then the orderer maintains a pool of outstanding transactions. So it would create a block, and then it would send completing block according to the block size and time limit and the other parameters. And then, okay, so to whom the block is sent? The block is sent to validating peers. And there are validating peers, usually it's the same, validating and committing peers. So validating peers finally execute the transaction. Please note that endorsing peers, they simulate the execution of transactions. They try to execute the transaction, but they do not update the actual data. They maintain a shadow copy of the data in order to simulate the transactions and produce the RW sets. It's the committing peers that actually execute the transaction, and they do it by comparing the RW set with the current state. Now, what may happen? So again, the first step of verification happens at endorsing peers. And at this point, the transaction may be valid. However, by the time the transaction gets ordered and sent to the committing peers, the transaction may become stale, invalid. That's one of the reasons why the transaction may become invalid. Because the state, like at some point in the past, the data was not updated, so the transaction was valid. In the meantime, the data got updated, and now the transaction cannot be applied any longer. That may happen. And it's the committing peers that would discover this situation. In this case, they would abort the transaction, but the block has already been produced by the order. Order doesn't get to rewrite the block in this case. And this is one of the reasons why invalid transaction may become part of the block in Fabric. Next, I'm going to talk a bit about the evolution of consensus protocols in Fabric, which are used by the orderer. The first version of Fabric used the PBFT protocol, which is one of the most common implementations of the BFT protocols. It's a more complicated extension of Paxos. It was proposed in the 90s by a professor from MIT who later got the Turing Award, Barbara Liskov. Up until today, it's one of the commonly used BFT protocols with the open source implementation and so on. By version 2.0, PBFT was not entirely replaced, so I should explain the progression. Each version of Fabric came up with the default and recommended implementation for the orderer. However, each version of the Fabric also maintained several alternative implementations. Like always, in Fabric, there are always alternative implementations for everything. So when Fabric 2.0 came out, the default implementation was using Apache Kafka. However, it was still okay to switch to PBFT. Now, Fabric version 3.0 came out with Raft as the default implementation. Raft is it's a protocol similar to Paxos. It does not tolerate Byzantine failures. So why did the Fabric abandon Byzantine resistance between version 2.0 and 3.0? Because the applications, the clients of Hyperledger Fabric were complaining about the speed of transactions. And Raft is much, much faster than BFT protocols. Raft is considered, in practice, the fastest consensus protocol today, even though there is not much difference between Raft and Paxos in terms of the performance. But of course, by that time, it was still possible, so the default was Raft, but it was still possible to use PBFT. And in the latest version of Fabric, which is 4.0, they switched to what's called Smart BFT, yet another BFT protocol, which is an improvement over PBFT. So they finally, in version 4.0, they abandoned PBFT completely. And of course, being a non-Byzantine tolerant protocol, Raft tolerates a failure of up to half of the nodes, while Byzantine protocols tolerate failures of up to 1/3 of the nodes. Okay, what about performance? Fabric is the blockchain, one of the blockchains with the fastest, with the best performance in terms of both throughput and latency. So a typical throughput is in the order of thousands of transactions per second with 100 millisecond confirmation time. Yeah, I should have mentioned earlier, perhaps it should be clear by now, but it's still worthwhile to mention it explicitly. So PBFT, Smart BFT, Raft, they are all deterministic consensus, final consensus. So again, what does it mean? It means that once confirmed, a transaction is never overwritten. So there is no rollback. And that's a difference from the probabilistic consensus in both Bitcoin and Ethereum and many other open cryptocurrencies. So 100 millisecond, order of 100 millisecond confirmation time. So that's quite good, but of course the exact numbers, I'm not giving you the exact numbers, I'm just giving you the order. Why? Because the exact numbers can vary a lot. They depend on a lot of factors. Okay, which factors? The version of Fabric, The version 3.0 is much faster because of Raft, but also the smart BFT is faster compared to the earlier versions of BFT. It depends on the consensus protocol used. It depends on the relation between the input transaction rate and the block size. Right, so it has been shown that for a given block size, increasing the throughput rate, the transaction rate, the input transaction rate, improves the performance up to a certain degree, up to a certain point, and then there is a threshold. And if the input transaction rate exceeds the threshold, the performance sharply falls down, or falls off. It also depends on whether we are running, or depends on the network, whether we are running Fabric in an optimal environment or in a more realistic deployment where failures may occur. And again, highly configurable, so there are numerous tweaks and optimizations, and they all exhibit different trade-offs in terms of the performance. So let's talk a bit about smarter contracts in Fabric. Smart contracts in Fabric, as I mentioned, are quite different from those in Ethereum. So there is no virtual machine in Fabric. Why? Because there is no need to standardize gas consumption, right? And another reason, okay, how do we make sure that the same transaction, when executed in different places, would reach the same result? That problem becomes that problem has been researched for many years. It's much more difficult in an open environment compared to a consortium environment. So effectively, Fabric does not resolve this question. It allows each program, each smart contract to run in a Docker container. And that's the default mode of execution in Fabric. So like the virtualization is different. I mentioned no use of gas. There is also no need for a dedicated programming language. Please recall that Solidity has several features which are very specific to the use of gas, for example. We know that, like the view keyword. View keyword means that the function is a getter and does not consume any gas. So there is no need for such dedicated language in Fabric. So in Fabric, contracts are supported in general purpose languages. Not all general purpose languages, but several general purpose languages. Another point that a smart contract in Ethereum must be verified on every node, or at least there must be sufficient number of validators. That's not the case in Fabric. In Fabric, a transaction and a contract not necessarily executed on all nodes. First of all, there is a channel, so it would only be executed within a given channel. But even within a given channel, not necessarily all participants in that channel would be running the contract. There could be a subset of validators. And another interesting point about contracts in Fabric is that they are managed in packages. So contracts in Ethereum are relatively small, as we saw. And each contract is more like a standalone unit. While contracts in Hyperledger are supposed to be full-fledged programs, they are much longer. So instead of talking about one contract, we are talking about package of contracts acting together as a single application. And therefore, smart contracts in Fabric are managed in packages. Those packages are called chain codes. And the advantage is that the configuration is given on a per chain code basis rather than on the per contract basis. So you configure packages instead of individual contracts, and that means less work for the deployment administrator and also for the programmer. Okay, the table here just pretty much summarizes what I said. Turing completeness. So Ethereum and Fabric provide both Turing completeness. Languages. So Ethereum supports several languages such as Viper, but Solidity is the most popular one. In Fabric, what are the popular languages for writing contracts in Fabric? Golang, Java, and Node.js, JavaScript. Who executes the contracts? So in Bitcoin it would be full nodes, in Ethereum it would be full nodes, in Hyperledger Fabric it's specified by endorsement policy, actually. So a subset of the endorsing peers and some of the committing peers. And the execution environment is a Docker container. So this table is quite big. It summarizes comparison between different blockchain platforms. So it's taken from this paper. So features, state tracking approach, Bitcoin, UTXO, Ethereum account balance. In Hyperledger Fabric is application dependent. We are not considering IOTA yet, because there would be a separate lecture on IOTA, I believe, tomorrow. The structure of data. In Bitcoin, sequence of block, sequence of block, sequence of block with transaction. Okay, here no difference. Maximum block size. In Bitcoin, it's 1 megabyte. In Ethereum, it's determined by the gas limit. In Fabric, it's configurable, as always. So different deployments will have different block sizes. On disk storage. So the ledger is stored as multiple files in all three systems. And state-related storage in Bitcoin UTXO set is stored in a level DB database. In Ethereum, there is very elaborate storage. And in Fabric, we're all state in the level DB or CouchDB. And then additionally, there is block index in the level DB. In memory storage, it's also quite educational how they manage in memory storage. So in Bitcoin, the block index database is in memory, UTXO cache is in memory, and could be also Merkle tree of transactions. In Hyperledger Fabric, there is interest in management of peer cache, but otherwise, again, there are different mechanisms and it's application dependent. Okay, so that was about Fabric. Now, what can we say about Sawtooth, the other system? Sawtooth is yet another ledger. It's the second Hyperledger project to reach maturity. Well, by now, the other projects are also quite mature. It's also permissioned, mostly. It's also intended for consortium blockchain. So in what way is it different? There are several differences which are actually not very significant compared to Fabric. The first difference is that it's written partially in Python, and it also supports smart contracts in Python, because Fabric was pretty much against Python because of the performance, while Sawtooth saw it as a weakness because Python is a very popular language, so they saw the need to support it. Well, they support it, but as a result, of course, because they use Python, sort of is noticeably slower than Fabric. However, there is something which it supports in terms of the performance, which Fabric does not, and that's parallel execution of transactions. So please recall that in Fabric, all transactions are serialized by the orderer. In sort of the consensus mechanism is different, and it allows for non-serialized parallel execution of transactions with perhaps slightly reduced security guarantees, but better performance in that sense. So each transaction is executing slower because of Python, but together they may be better sort of parallelized, and therefore the collective execution may be faster. Sort of is one of those systems which uses proof of elapsed time based on a trusted execution environment. And that's another element. So trusted execution environment has benefits and also disadvantages. It's costly, right? So do we want to force everyone to buy trusted chips for the trusted execution environment? So in SOTO, you can do that. In Fabric, they say resoundly no. There are also minor differences. So Fabric is purely permissioned, while SOTO can also run in some restricted permissionless environments. So they also have some technology to this extent. And that concludes the second lecture today. Thank you for the attention. And if you have any questions, please ask. 1, 2, 3. 1, 2, 3, 4, 5. Hello. Alright, sorry for the technical hiccup. Thanks for fixing. All right. We now start the last lecture for today, and this lecture is dedicated to yet other two systems called Ripple and Corda. And again, there is very little in common between the two systems, we just package them in a single lecture. So what are Ripple and Corda? Okay. Okay. So Ripple is one of the earliest cryptocurrencies, and today it's number 4 by the market cap. But it was number 2 by popularity before Ethereum was launched after Bitcoin. Well, Corda is, I already mentioned Corda in the lecture on Hyperledger. Corda supports a totally different paradigm related to blockchain. And it's intended for developing blockchain application, doesn't even have its own token. So let's talk about Ripple first. In Ripple, again, there are different roles for nodes. There are users doing financial transactions. There are market makers, and the market makers is essentially a credit network of trusted banks and subsidiaries taking responsibilities for transactions. So please note, it's totally different from everything we've seen before. They said no centralized control. Well, and usually banks compete with cryptocurrencies. In Ripple, banks participate in the system. So it's a credit network of trusted banks and subsidiaries. And then we have validating servers, which are running consensus on the ledger. And the system is permissioned and tightly controlled. So Ripple is an interesting case in which the ledger is open for everyone to see, but there is a small subset of validating servers which are responsible for running consensus and extending the ledger. So how does it work with respect to the peer-to-peer network of market makers? So you can see here that there are two users, A and B, and the user wants to transfer, say, $100. User A wants to transfer $100 to B. So the idea is this payment, but how is it implemented? There is a need to find the routing path of financial institutions which are willing to route the transaction. And as a matter of fact, this is what happens when you say transfer funds like long distances. If you transfer funds, say, from some small bank in India to a small bank in say, Brazil or Norway, like the other part of the globe, what happens is that the transfer is not direct. So usually, like the small bank would send the money to a larger bank, and the larger bank would connect to a network, and then it would reach the main bank of Norway, and from the main bank of Norway, it will go to the small bank where the account is registered. So this is what happens today. But of course, what happens today, like this path, is opaque. It's not visible to the users. When I make a transfer, I don't know the path that the money takes. I only know the end result of the transfer. In Ripple, you get to see the entire path of financial institutions which are willing to route the funds. And not only this, the path is calculated by the system. So it can be dynamic and adaptable. There is also another interesting aspect. They can transfer, for example, they can transfer dollars, not the Ripple currency. Of course, like it's simplified if they are transferring Ripple currency, because then we can check the accounts. But they can also transfer dollars, or they can transfer bitcoins using Ripple. How? This is the example with dollars. So they introduced the concept of IOU transactions. So what happens is that every financial institution has a trust, has a like limit of trust towards every user and every other financial institution. So you can see here, institution U1 has trust of up to $250 for A. So as long as A transfers a smaller amount of funds, or wants to transfer, it's okay. And then U2 has a trust of up to $130 towards U1. So, okay, so what happens when A transfers the funds? This amount is, it's like a credit, right? So this amount is deducted from the credit amount. And this happens on every step in the path, which needs to be coordinated. And by the way, the selection of the path needs to take the credit frame into account. For example, here you see the trust is $90. So it's impossible to use this path in order to transfer $100. So the calculation of the path is one interesting aspect of Ripple. But at the end, it allows Ripple to act as a bridge between currencies. So we were talking about interoperability of currencies in one of the lectures. So Ripple was the very first bridge. Today we have many more, but Ripple was the first one. And it's still functioning as a bridge. Now, okay, so that was the peer-to-peer peer-to-peer architecture of Ripple. But Ripple also has consensus, like a small number of servers performing the consensus. Well, small number. Small number means up to 100, not up to thousands. Still, so 100 is not such a small number. How do they do that? All validating servers execute 3 asynchronous phases: collection of transaction, consensus on transaction, and ledger closure. During the collection phase, the servers collect new transactions from the network, and each server verifies every transaction, including the routing paths. And then, towards the end of the phase, the server constructs a proposal that includes every verified transaction received during the collection phase. Now, during the consensus phase, proposals are continually exchanged, and what's interesting is that during the consensus phase, new transactions are still arriving. So, at the end of collection phase, just the first proposal is being formed, but those proposals, they are being extended all the time because new transactions are arriving, even during the consensus phase. And what's interesting is that even though proposal is like is for a batch of transaction, but the voting on every transaction counts individually, right? So if a proposal includes a transaction, this counts as a vote for that transaction. So the votes for each transaction are counted separately. And when the transaction receives votes from 80% of the servers, it becomes confirmed. And once all of the transaction, or each transaction in the proposal gets confirmed by 80% of the servers. We start the third phase, which is ledger closure. And the closure procedure produces a new ledger. So it's different, again, from Bitcoin or Ethereum. In Bitcoin or Ethereum, we have a single chain of blocks, right? In Ripple, instead, there is a chain of ledgers. And each ledger would include many transactions. And then, like, the whole thing works in a loop. The 3 phases, right? After the previous ledger is closed, we start the new collection phase. So the duration, of course, of the collection phase is something that's very important for Ripple, because if the collection phase is too long, then it takes too much time to confirm transactions. But if it's too short, then each ledger will end up with many ledgers and many small ledgers. And that is not good for performance. So how does it perform in practice? Most ledgers are finalized in a few seconds. However, some ledgers take up to a minute to close, though almost 99% of the ledgers are closed in less than 20 seconds. So then 99% percentile. So the performance is reasonably good. It's definitely much faster confirmation compared to Bitcoin. But of course, like, it's difficult to compare because Ripple is intended for a completely different purpose. Ripple is not effectively competing with Bitcoin. It's not a cryptocurrency in the same way. Well, it supports its own cryptocurrency. But it's mostly for transfers between banking institutions. So this is the overview of Ripple. And again, there are many details in which I'm not going. Now, let's proceed to the second system, which is Corda. In one of the first lectures, I was talking about the advantages of using blockchain. And I said that essentially that's one of the generally perceived advantages of blockchain is to enable parties who do not fully trust each other to form and maintain consensus about the existence, status, and evolution of a set of shared facts. So that's true about blockchain in general, but originally it was penned by I believe, Richard Brown, who is behind Corda. So how does it work in Corda? So the way it's implemented, I mean, the paradigm in Corda is very, very different from any other blockchain system we've seen so far. There is no sequential ledger. There is no even like some DAG, directed acyclic graph of transactions. Instead, there is a collection of facts. So each circle that you see here is a fact. And the fact could be shared not necessarily between everyone, every participant in the system. For each fact, there could be a different set of nodes sharing that fact. So you could see that, for example, these two facts are overlapping, which means that the set of nodes sharing these facts are overlapping. And here you see some nodes would be privy to all three facts. But in general, facts are confidential, so and encrypted, and they are like protected, so by access control. So, what are examples of shared facts? Two banks may agree that one bank owes certain amount of funds to the second bank, and that this amount needs to be repayable on demand. Another example, that this is a cash demand deposit. Two banks may agree that they are parties to some credit default swap. Two parties may agree to sign a contract. So contracts also play a very important role in Corda, but it's a different concept. It's similar in the sense that instead of the legal contract with the intermediary, we have an electronic contract, which is stored on the chain. That is similar. But of course, all the execution of the contracts, that is totally different in Corda. Because the contract is just attached to a particular fact. So the whole storage in Corda is a collection of facts. Now, those facts are I'm going to talk about it a bit soon. The facts are also cryptographically secured, so in that sense it's similar to blockchain, but the way it's done is different. Okay, but two banks agree that Bank A is obliged to deliver something within 3 days in exchange for a cash payment. So all kinds of financial agreements are represented as facts in Corda. And the whole system is intended, so the system is mostly intended not for individual users, but for financial institutions. Well, of course, individual users can also be part of the system. It's like a peer-to-peer network of financial institutions who do not necessarily fully trust each other. So what's the similar? Let's place Corda in comparison to other blockchain systems. How is it similar? It's similar because there is no centralized party controlling the workflow. There is no one organization which would control the storage of all the facts. Instead of it's a peer-to-peer system. It's similar because it uses cryptographic primitive to ensure immutability of facts. Though the facts is, well, it's a bit similar to ledger, to the sequential ledger, in the sense that the facts cannot be easily tampered with, and the facts may have some complicated dependencies, in which case a later fact would be cryptographically linked to the previous fact. And that also gives extra immutability protection for the facts. It's similar in the sense that validity of transactions is being checked, but of course it can only be checked within the validators who get access to a particular fact. And usually it's a small number of validators. It's similar in the sense that there is an agreement protocol. Before the contract, before the fact is getting signed, there is a consensus protocol on the fact. It's similar in the sense that there is a contract resolution here, there is no branching in Corda, but could be some disputes between the participants. And those disputes need to be resolved, and there is an additional mechanism for resolving the disputes on the facts. Similarly to Hyperledger, it uses a permission peer-to-peer network between the participants. And the transactions are generic, so they're not necessarily financial. It's not only transfers. The facts can be anything. However, it also has significant differences compared to other blockchains. So no global sharing of data. Only parties with legitimate need to know can see the data within an agreement. So it's on the need to know basis. There are no blocks, and consequently no sequence of blocks. And the consensus between participating organizations at the level of individual deals. So it's not a global level of the system. It's not like a order in Fabric which orders all transactions, even maybe within a given channel, but still all transactions within the channel. Here, like, the scale of consensus is much smaller. There is provision in the Corda design to enable supervisory observer nodes, which would be allowed to observe the compliance of financial transactions with the regulations. So the design of Corda is aware of specific regulations like Know Your Customer and similar, and would support those regulations. So how consensus is achieved? It's achieved at the level of individual deals, but what's the mechanism? So Corda supports a variety of consensus mechanisms at a small scale. However, most of those mechanisms, again, based on Byzantine fault tolerance between a small number of participants. Corda records an explicit link between human language legal prose documents and smart contract code. And in fact, well, it's not specific to Corda, but one of the very promising research directions is how to take legal document from lawyers and do automatic translation of the legal prose in the document to the executable code and create a contract based on the legal prose. So that's generally one of the important areas of research. And Corda plays significant role for this direction because it has an emphasis on the legal documents. And by itself, Corda has no native cryptocurrency. The transactions, the agreements about the facts could be not necessarily financial, well, usually they are, but those financial agreements, they usually transactions in real currency, in fiat, not in cryptocurrency. Yeah, I'm sorry, I'm not even sure, like, I don't know why it's so blurred. It's not on my screen. So I guess it's very difficult to see what's in the picture. But the picture is supposed to illustrate several aspects, right? So essentially it shows how agreements are stored. So these two institutions are partners to the agreement, and then in agreement, always has some embedded reference to the contract code, and also embedded reference to the legal prose. So an agreement usually includes reference both to the legal documents and to the programmatic contract. So, and the two are connected together. That link is very important for Corda. And yeah, so that the content of the contract can be anything, right? So it's illustrated here, but it's not so important. Of course, Corda also places significant emphasis on reusability of code and reusability of smart contracts. So developed once, but used for many. So it's pretty much standardized because most of the applications for Corda serving similar purpose of financial agreements, right? So both the legal prose may be standardized. There is a library of legal prose, and there is a library of programmatic contracts. Yep, so this is the end of this lecture that covered repo and Corda. I would like to thank you and welcome. Questions are welcome as always.